So, this is the procedure for the Breusch and Godfrey test. You have to estimate the model, you have to get the predicted value of the error term, then you have to also create the predicted value of the previous period lag error terms, and then you need to regress the UT on its previous values and also on the explanatory variable, right, the explanatory variable. And then if you do so, this is the result. All right, this is the result. Now, in Stata, you don't need to implement the test always manually. Stata, there is a specific command. If you estimate the model reg wage and productivity, then immediately after estimating the model, what you need to do, you need to specifically mention a command for this Breusch and Godfrey test, which is estat b Godfrey. So, this is the command. I will first write the command here, so that you should not forget. So, this is the Stata command, estat b Godfrey. This is the Stata command. Stata command estat space b Godfrey. Okay, that is the command. If you put, then you will get this result. Now see, the chi-square value is 32.20 and again highly significant even at what percent. But there is a difference between the test what we have conducted and slight difference what Stata is reporting. See, in our manual result what we did, we have specified 6 lags, but Stata is reporting P equals to only 1. What is the number of lag? Only 1. Now your question is, you are interested in testing higher order lags. That is why we are going for Breusch and Godfrey test, but Stata is reporting only result with 1 period lag. It is as good as the Durbin-Watson test statistic. Why this is so? Okay, why this is so? Now the reason is, even though Breusch and Godfrey can detect higher order autocorrelation, if you look at your result, see, apart from U1, that means apart from the first order lag, U2, U3, U4, U5, U6, all these coefficients are actually insignificant. All these coefficients are insignificant. That is the reason Stata is reporting the Breusch and Godfrey test with only 1 period lag. Had there been higher order lag, Stata would have considered those number of lags. Let us say in the data you have lag up to 3 periods, then Stata would have reported the result with lag equals to 3. But here only U1 is significant, that means UT minus 1 hat is significant, U2 minus 2 hat, U2 minus 3 hat, UT minus 2 hat, U3 minus UT minus 3 hat, all are insignificant. Okay, since all are insignificant, Stata has not reported the result with higher period lag. Stata has reported only this. This should be your conclusion, right? So now what we have learned? We have learned Durbin-Watson test. We have also learned the Breusch and Godfrey test to test for higher order autocorrelation. Now the next question that comes to our mind, that once you detect autocorrelation, what is the solution? Okay, what is the solution? So, solutions for autocorrelation. Solutions for autocorrelation. All right. Now, the first solution is, what you need to check is, first you should check, whether autocorrelation is pure or due to model misspecification. Okay, model misspecification. So, that means when we were running this model yt equals to alpha plus beta xt plus ut, where yt is wage and xt is productivity, it may so happen that in the true model there is non-linearity between wage and productivity, and that is actually leading to this autocorrelation problem. So, that means we have to check whether yt equals to alpha plus beta 1 x 1 t plus beta 2 x 2 t plus ut. Sorry, this is not 2 t, I will say this is beta 2 x 1 t square. So, that means I am including productivity as well as square in the model to check whether there is any model misspecification. If the autocorrelation is due to model misspecification, then once you correct that by a square term, your autocorrelation problem will get automatically resolved. You do not need to do anything else. That is why econometricians, they first say that before applying any other medicine, you just see whether autocorrelation is pure or due to model misspecification. So, how will you do that? You need to generate the productivity square. So, let us say I am giving a different name, which is let us say x, and how I am defining x? This is nothing but productivity square. Okay, productivity square, and then automatically my x variable is included. So, now what you need to do? Reg wage, then productivity, and you also include your x. Okay, x. This is the model now I have included. Now, interestingly, you see the productivity is positive, coefficient of productivity is positive, but productivity square is actually negative and significant. That means, as productivity increases, wage first increases, but after some point of time it is coming down, it is not increasing that much. So, there might be some reason behind this, that means some kind of non-linearity might exist between wage and productivity. You might explore the reason, I am not talking into that part here. So, what I will do now, after this model, once you estimate this modified model, let us see what is the value of the Darwin-Watson test statistic. Sorry. So, DWSTAT. Now, see the productivity after improving productivity square, the test statistic, Darwin-Watson test statistic value, it has improved a lot from 0.12292, it is now 1.02, 1.02. So, it has improved, but still it is still lower than the Darwin-Watson lower value. What was the lower value we were discussing? If you remember, so look at, it is 1.39, and how much value you are getting here? It is 1.02. So, it is still lower than the lower limit of Darwin-Watson test. So, that means the autocorrelation is not due to model misspecification, it is actually a pure autocorrelation. Okay. Pure autocorrelation means the other reasons, that inertia and other things, that means the time series macroeconomic variables, they exhibit business cycle, so on and so forth, and that is why this autocorrelation is actually existing in the data. So, that means by modifying the model we cannot solve autocorrelation problem, we need to think about other method, and now we will discuss about other method of solving autocorrelation problem. Okay. So, we need to, the second method is called, row differencing. Row differencing, where rho is the autocorrelation coefficient. So, your model was yt equals to alpha plus beta xt plus ut, and ut follows, ut equals to rho ut minus 1 plus epsilon t, that is your data generating process. So, what you need to do here, that you need to first take the difference of this. So, that means yt minus 1 should be equals to alpha plus beta xt minus 1 plus ut minus 1. Then what you need to do, yt minus rho yt minus 1 equals to, so this is alpha minus rho alpha, okay, alpha minus rho alpha. So, I am multiplying, let us say this is equation 1, this is equation 2, and I am multiplying equation 2 by rho, and then I am taking 1 minus 2 into rho, that implies yt minus rho yt minus 1. This would become alpha minus rho alpha. So, that means if you take 1 minus rho into alpha plus beta into xt minus rho xt minus 1 plus ut minus rho ut minus 1. Let us say this is 3, and then apply OLS in 3, that is the procedure. So, that means what I am saying, while OLS was not applicable in equation 1, how come OLS is still applicable in this modified equation after row differencing? Because what is ut minus rho ut minus 1? From this, if you look at the data generating process for the ut, this says that ut minus rho ut minus 1 is actually epsilon t, and epsilon t follows all the assumption of classical linear regression model. That is the reason this error term is actually the classical error term, it does not show any autocorrelation problem. Okay. So, this is the row differencing method. So, that means you need to you need to transform your dependent as well as independent variable. How? If your dependent variable is y, then the modified dependent variable would be yt minus rho yt minus 1, and your independent variable would be transformed as xt minus rho xt minus 1. Okay? But the point here is, this row differencing method is applicable only when rho is known to you. Rho is known to you. That is why row differencing is applicable when rho is known. Rho is known. Okay? If you know the row, then it is fine. But if you do not know the row, what will happen? Okay? If you know, then you put the specific value of row. If you do not know, then what we need to do? We need to assume a specific value for row, right? Now, if we assume row equals to 1, then what will happen? Okay? Then what will happen? So, that means your row transforming equation was yt minus rho yt minus 1 equals to 1 minus rho into alpha plus beta xt minus rho xt minus 1 plus ut minus ut minus 1, sorry, rho ut minus 1, ut minus rho ut minus 1. So, if you put rho equals to 1, that means if we assume there is perfect first order, perfect positive autocorrelation, then this equation will become yt minus 1 equals to beta xt minus xt minus 1 plus ut minus ut minus 1, just by putting rho equals to 1, and this equation is called first difference. So, this is called first differencing. So, first differencing is a solution to solve autocorrelation problem when rho equals to 1, right. So, generally econometricians they say that when d is less than r square, they say apply first differencing. Okay. All right. Now, what we need to do? We need to transform the variable as yt minus 1 and xt as xt minus 1, right. So, what we will do? We will transform the variable. So, we will say that gen d wage, this is d wage I am writing, equals to d dot wage. So, what is the command I am using? Earlier I was using L for lag and D for difference. So, the moment I say gen d wage is basically a name, and d dot wage means wage t minus 1, that means basically yt minus yt minus 1. I have created the first difference. Similarly, gen d prod equals to d dot productivity. So, I have created the two first difference of wage as well as productivity. And now, if you regress d wage on d productivity, then we will see. But before we do that, we have to again look back to our model. See, in the first difference equation there is no constant term. Okay? The constant term gets cancelled when you put rho equals to 1. So, in any first difference equation you have to keep in mind, whenever you run first difference equation, you should not include constant term in the model. So, now you reg d wage on d productivity. Sorry, I have given a different name, reg d wage on d prod, because that is the name I have used. Sorry, again I made a mistake, I put constant. So, reg d wage d prod, then no cons. Alright, this is the command. Right. Now, here again after running this first difference equation, what is the Darby-Watson value? Darby-Watson value has improved a lot, 1.5096 in the first difference. Okay. So, the Darby-Watson value is 1.50, which is actually now if you go back, then you will see that your value was Darby-Watson lower value was something around 1.34 or something. So, that means it has now improved a lot, right. So, severity of autocorrelation problem has improved a lot if you take the first difference. And is first difference applicable here? That means 1.50 is it what is the sorry, I have made it ulta. This should be greater than this. No. This is in the original equation. In original equation. So, in original equation, if you look at the original equation, that means this equation you have to see. Reg wage and productivity, where we have run that equation. If you look at reg wage productivity, reg wage and productivity, and then dw stat, yeah. So, this is lower than the R square. This is lower than the R square, and first difference is applicable. Okay, first difference is applicable. But the only problem with the first difference is that we are specifying a specific value for rho hat, which is 1, and also the moment you take first difference, the interpretation of the coefficient, we are interested to see the impact of xt on yt, but ultimately what we are getting, the impact of delta yt on delta xt. Okay, that is the problem. right. But anyway, the severity of autocorrelation is largely reduced. The next question what we need to do is, if we do not know the value of when this rho is unknown, what actually you can do instead of putting rho equals to 1, there are two ways by which you can get rho. See, if you recall, we have a relationship like this is 2 into 1 minus rho hat, right. So, the moment you know Darwin-Watson test statistic, using this relationship you can get rho hat. So, you estimate the model, get your Darwin-Watson test statistic, and then put the Darwin-Watson value here and get your rho hat. That is method number 1. Method number 2 is, you estimate the model, get your UT hat, and then run this regression, reg this equals to rho UT minus 1 plus epsilon t. So, that means if you regress UT hat on UT minus 1 hat, from there also you will get rho hat. That is also possible. So, when rho is unknown, these are the two ways by which you can get rho hat. But please keep in mind, the relationship D is almost equals to 2 into 1 minus rho hat is applicable when you have sufficiently large number of time periods. Okay. Here the number of time periods is 40, which is large, but if you have 10-15 years data, then this is not actually applicable, this method. You have to use the method number B, this one. You can simply regress UT on UT minus 1 and get your rho hat. Okay. Now, econometricians they say sometimes that in this method, how do you know that the rho hat is the best method? Because you estimate the model, regress UT hat on UT minus 1 hat, collect that rho hat and using that rho hat to transform the variable. So, there is no guarantee, there is no guarantee that this rho hat is the best. That is why they sometimes suggest to iterate this procedure for 1 or 2 couple of more rounds. So, and that procedure is called Cochran-Orcutt procedure. Cochran-Orcutt procedure. What they say? You run this regression, yt equals to alpha plus beta xt plus ut, and then you regress ut on rho ut minus 1 plus epsilon t, and then from there you collect your rho 1 ut minus 1, rho 1 hat. Then what you do? This is step 1, this is step 2, then in step 3, what you do? You transform your dependent and independent variable with this rho 1 hat. Xt minus rho xt minus 1. So, I have changed my this and this, and let us say this is called yt star, and let us say this is called xt star. Then what I need to do? I need to regress this yt in step 4, reg yt star on xt star and get ut star. Then what you need to do, again run ut star hat equals to rho 2 ut minus 1 plus epsilon t and get rho 2 hat. Again you take this rho 2 hat to transform your dependent and independent variable. So, that means you will get rho 1 hat, rho 2 hat, rho 3 hat in every successive iteration, and I will stop when the two successive periods rho hat is actually equal, and this will continue until rho 2 hat minus rho 3 hat equals to rho 3 hat, or rho 2 hat and the rho 3 hat, this difference is less than 0.001. Okay, and I will take that rho hat to transform the variable. Okay, I will take that rho hat to transform the variable instead of using this rho 1 hat which is coming in the first stage. Is this clear? So, this procedure, Cochrane-Orchard procedure, is nothing but repeating the procedure for couple of more rounds, more iteration, and then take that particular row when two successive periods rho hat actually converges to each other, or the difference between the two rho hat is less than 0.001. Alright, and in the process, how will you do that? In the data, if you want to apply this Cochrane-Orchard procedure to correct your yt and xt, transform your yt and xt, and then run the regression, problem of autocorrelation will come down a lot. I will show you the command. This is again a specific command, praise praise your dependent variable wage, independent variable productivity, and then you have to put CORC. This is the command for transforming your dependent and independent variable and then running the regression using Cochrane-Orchard procedure. Sorry, praise wage produc productivity in CORC. This is the command. Now look at what Stata is doing. Stata is running so much of iteration, 17 rounds of iteration, and then lastly Stata is taking 0.8913 as the best row, okay, and that row is used to transform your yt. That means yt is now yt minus row yt minus 1, xt is now xt minus row xt minus 1, and then the regression is run using this row. This is the regression output, and you see the Darwin-Watson original value which was 0.122, now it is 1.60. So, you have solved actually the autocorrelation problem, and you have got the best result. This is how you can solve your autocorrelation problem by a generalized method of row differencing suggested by Cochrane and Orchard procedure. Okay, Cochrane and Orchard procedure. So, with this we are closing our discussion on autocorrelation. We have discussed about what is autocorrelation, what are the consequences. Consequence is basically the standard error gets disturbed, efficiency property get disturbed, and as a result of which you have problem in your hypothesis testing. And then we have discussed about how to detect autocorrelation using Durbin and Watson as well as Breusch and Godfrey test. And lastly, we discussed about solution, row differencing and fast differencing. Okay, row differencing and fast differencing. And then we lastly discussed about Cochrane-Orchard procedure, which is an iterative procedure to get the best row to transform your dependent and independent variables. With this, the discussion of autocorrelation is over. Thank you.